Okay, morning everyone and welcome. So this morning I'm going to be talking to you about the evaluation and the interaction and the release of ethyl format within a bio-friendly polymer matrix for post-harvest fumigation. So I'm going to quickly do a brief introduction which would follow with the aim of the project. I will discuss some of the results that we've obtained so far, and I will end off with the conclusions and future studies. So food packaging plays an important role, as you all know, to keep our products fresh, especially during storage and transportation. However, the food packaging can be classified as two entities, either as an intelligent type of packaging or as active packaging, and the one that we would be focusing on is active packaging. Due to the restrictions that are obtained from using conventional type of fumigants, as you know, like methyl bromide, because of ozone depletion, we are forced to look at other alternatives, and one such alternative is ethyl formate. So why do we choose ethyl formate? We know that ethyl formate is a natural occurring product. It's known for insecticidal properties, antimicrobial properties, and once it breaks down, it actually forms formic acid and alcohol, and some studies have shown that it can possibly be used as a fumigant. However, with any great thing, there are some challenges. So there are end-use applications of ethyl format because of the volatility and flammability, which makes it dangerous to use. So to improve the stability, you can either use a precursor of ethyl format or you can incorporate it into a polymer matrix. So if you use a polymer matrix, you need to bear in mind that it needs to be something that is non-toxic and biodegradable, as we are working in the food industry. So two polymers like that is polylactic acid and polyethylene glycol. So incorporating that into with the ethyl format precursor, we can trigger the release, so essentially we can have ethyl format that is being released. So to obtain this, we divided the project into three parts. The first part was to look at different types of ethyl format precursors, which was followed by the second part, which is to incorporate that precursor into a polymer matrix to further stabilize the whole process. And then the third part was then to evaluate the release of different quantities of ethyl format from these polymer matrices. And the most difficult part of this project is actually finding the possible great delivering system with regards to the polymer matrices. So we first looked at three types of ethyl format precursors. We looked at adipic acid, trimesic acid, and citric acid. And upon characterization, we could see that the citric acid precursor wasn't really stable. So we decided to only focus on adipic acid and trimesic acid for the rest of the studies. The next phase consisted of looking at the biodegradable polymer system. And firstly, we look at polymer films. The most crucial part when looking at the films was the incorporation of the ethyl format precursor into the polymer and then creating the film. And the reason why that is the most crucial step is that you want an even distribution of the precursor within the film so that you can have the most effective release of your ethyl format. The second part was also looking not just at films but at other possibilities like microspheres. And the reason why we wanted to look at microspheres is that the overall surface area can be improved by using rounded spheres instead of the films. And if we have a higher surface area, we can essentially load more ethyl format within the particles, which means a more effective way of releasing the particles. To better control it further, we increase the ratios and we made porous particles so that we can release the ethyl format more effectively. And upon further investigation, we managed to encapsulate polymer particles within each other, and this is very promising as this can ensure longevity release over a period of time, which is great. However, the absorption and the encapsulation of the ethyl format was really difficult because of the volatility of the ethyl format. So the third part of that of the project was to look at GC-FID analysis in terms of detecting the amount of ethyl format that can be released. So we managed to set up a calibration curve with a R-square value close to 1, and that enabled us to detect the release of the ethyl format from the polymer films. And after long investigation and some trials, we could see that the adipic acid precursor actually gave the most consistent results, and that would be the best one to go forward with. So to conclude, we did manage to incorporate ethyl format precursors into polymer matrices that can be stabilized. We can monitor the release of the ethyl format, with confocal fluorescent microscopy as well. We are busy with large-scale testing right now, and the trial testing of effectiveness should be conducted. And I would like to thank the following people for their support, and Hortgrove for funding, and Stellenbosch and staff for their facilities. Thank you, and if you have questions, please come see me.